Section 32 of the Science History of the Universe, Volume 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. The Science History of the Universe, Volume 2, edited by Francis Rolt-Wheeler, Geology. Chapter 16, Mining and Metallurgy. Among the many minerals which constitute the crust of the earth, there are some which are of such character and occur in such quantities that they possess commercial value, and it is profitable to separate them from their neighbors and apply them to the service of mankind. The process employed in the extraction of these useful minerals are classified under the term mining. The origin of mining retreats into such antiquity as to be most obscure. It is certain, however, that the Phoenicians and Egyptians at the earliest periods of history had an abundance of metals. The Egyptians had mines of copper, silver, and gold in productive operation both on the Ethiopian and Arabian border. The Sinaitic Desert contains the ruins of mining works, probably operated by the Egyptians. Abraham found gold and silver in use among them. In the time of Alexander, gold, silver, copper, and iron were obtained in Ethiopia. In Asia Minor, the gold mines formerly owned by Croesus were worked down to the time of Xenophon, but Strabo says that in his days they were exhausted. The Athenians worked rich silver mines in Attica and gold mines in Thrace. Before the time of the Romans, mining was carried out in many parts of Western Europe. After the conquest of Caesar, the tin of Cornwall was shipped first to the Isle of Wight and thence to the coast of Gaul, where it was loaded upon horses and transported to Marseilles. The early Romans did not work the mines of their native land, but by their numerous conquests gained control of all the important mines of the ancient world. Traces of ancient mining in the United States are found to the copper region of Lake Superior and to certain districts in New Mexico. In both cases, the implements used seem to have been rude hammers of stone. It is evident that in ancient times muscular force, assisted only by applications of fire and occasionally by the power of water, was the miner's resource. A most suggestive picture of rude mining operations is given in the book of Job 28, 1-11, of which Conant's translation brings out the points very strikingly. For there is a vein for the silver and a place for the gold which they refine. Iron is taken out of the dust, and stone is fused into copper. He puts an end to the darkness, and he searches out to the very end, stones of thick darkness and of death shade. He drives a shaft forgotten of the foot, they swing suspended far from men. The earth, out of it goes bread, and under it destroyed is with fire. A place of sapphires are its stones, and it has clods of gold. Against the flinty rock he puts forth his hand. He overturns mountains from the base. In the rocks he cleaves out rivers, and his eye sees every precious thing. He binds up streams that they drip not, and the hidden he brings out to the light. Pliny gives a similar description of shaft-sinking operations. Quote, "Elsewhere, pathless rocks are cut away and are hollowed out to furnish a rest for beams. He who cuts is suspended with ropes. They go where there is no place for the footprints of man." The removal of surface material by sluicing was also practiced in ancient times in Spain. The Aztecs had an extensive metallurgical industry. They understood how to sink shafts and run tunnels, says John S. Hittel, how to wash gold from alluvial deposits, how to use the bellows and furnace in smelting the ores of copper, tin, lead, and silver, and how to cast metals. They had a little tin and considerable quantities of lead. The Quecans were not less skillful, and they quarried stone with veins of silver on a large scale. They alloyed gold, silver, and tin with copper, so that these metals must have been mined, and a complete knowledge of fluxes in the fusion of ores was known to them. Barbarism generally, which is often regarded as being coupled with the Bronze Age, was obviously possessed of mining, and not only of mining, but of smelting also. Before proceeding with any further discussion of the useful minerals, it is well to understand what is meant by the expression ore deposits. This is clearly set forth by Heinrich Ries in his Economic Geology. Quote, The term ore deposits, he says, is applied to concentrations of economically valuable metalliferous minerals found in the Earth's crust, while under the term ore are included those portions of the ore body of which the metallic minerals form a sufficiently large proportion to make their extraction profitable. A metalliferous mineral or rock might therefore not be an ore at the present day, but become so at a later date because improved methods of treatment or other conditions rendered the extraction of its metallic contents profitable. A few metallic minerals serving as ores, such as gold, copper, platinum, or mercury, sometimes occur in a native condition, but in most cases the metal is combined with other elements, forming sulfides, hydrous oxides, carbonates, sulfates, silicates, chlorides, phosphates, or rarer compounds, the first 5 of these being the most numerous. A deposit may contain the ores of one or several metals, and there may also be several compounds of the same metal present. The terms rich and poor, as applied to ores, are used with great frequency, although most indefinite and often meaningless. Under very favorable conditions, it is possible to profitably work an ore of given value at one locality, while if found under other less favorable conditions at another point, it might be almost worthless. The important ore deposits are not numerous. There are many other ores mined for the metal they contain, but they are either of small economic importance or occur in small quantities in nature. Iron is an abundant constituent of the Earth's crust, and yet few minerals are capable of serving as ores of this metal, and 5 ores supply the greatest amount of the world's iron: magnetite, hematite, limonite, siderite, and pyrite. Magnetite occurs in the United States, 1, as lenticular masses commonly in metamorphic rocks, 2, as more or less lens-shaped bodies in igneous rocks, 3, as sand on the shores of lakes and seas, and 4, as contact deposits, that is, those which form along the surface of contact of igneous and sedimentary rocks. The first class includes the most important deposits now worked in this country. The second and third groups run too high in titanium to have commercial value at the present time, and undoubted representatives of the fourth class of commercial value are not worked. There are some, it is true, which occur along the contact of an intrusive and sedimentary rock, but their origin is ascribed to meteoric circulations. Of all the iron ores, hematite is by far the most valuable, chiefly on account of its easier reduction, but also because of the greater richness of the known important deposits. Most of the deposits mined belong to the replacement type, that is, they are the result of the replacement of a fissure-filling material. Limonite may occur under a variety of conditions and associated with different kinds of rocks, but 2 important types are recognized, namely bog ores and residential limonites. The bog ores are formed by the precipitation of limonite in swamps, ponds, or lakes. Such ores are usually impure from an admixture of sand or clay which has been deposited at the same time, and are rarely of any thickness. They are of no commercial value in the United States, but are mined more extensively in Sweden and Canada. The residual limonites are a much more important class and are formed by the weathering of pyritiferous veins, or more often from the weathering of ferruginous rocks. Siderite is the least important of all ores of iron mined in the United States, both on account of the small quantity and its low iron contents. When of concretionary structure, with clayey impurities, it is termed clay iron stone. Pyrite, though widely distributed in nature, is not used as an iron because of the large amount of sulfur contained. Copper-bearing minerals are not only numerous, but widely, although irregularly, distributed. More than this, copper is found associated with nearly every variety of ore or ore deposit. Nevertheless, but few minerals serve as ores of copper. All the largest copper deposits in the world may be divided into 2 groups. 1. Deposits formed by ascending, circulating, probably hot waters, the ores being deposited in fissures, pores, spaces of brecciation, or sometimes replacement of the rock. And 2. Pod or lens-shaped deposits in crystalline schists, which may represent concentration of material from a disseminated condition in the surrounding rocks. The ores of lead and zinc occur very often associated with each other. Of these, galena is the commonest lead ore, while others are usually found where superficial oxidation of the deposit has taken place. Of the zinc ores, sphalerite, also known as blend, jack, or blackjack, is by far the most important. With few exceptions, zinc is constantly associated with lead, and at times, as in portions of the Cordilleran region, carries silver or even gold. Gold and silver are obtained from a variety of ores, in some of which the gold predominates, in others silver, while in still a third class, these two metals may be mixed with the baser metals, lead, copper, and zinc. Few gold ores are absolutely free from silver, so that a separate treatment of the two is more or less difficult. Gold occurs in nature chiefly as a native gold mechanically mixed with pyrite, or as a telluride, such as calaverite. Most of the gold and silver mined in the United States is obtained from fissure veins, or closely related deposits of irregular shape in which the gold and silver ores have been deposited from solution, either in fissures or other cavities or by replacement. Considerable gold and a little silver is obtained from gravel deposits. Some true contact deposits are known. Gold has been found to occur in rare instances as an original constituent of igneous rocks and also metamorphic ones, but there are no known deposits of commercial value belonging to this type. The gold and silver ores are sometimes grouped as one, placers or gravel deposits. These serve chiefly as a source of native gold, but may and often do contain a little silver, much of which is never separated from the ore in which it occurs. 2. Quartzose or dry ores, in which the gold and some silver are found in quartz gangue and are either freed or mixed with sulfides, commonly pyrite. 3. Gold and silver bearing copper ores. These are widely distributed throughout the United States and exhibit great differences in form and age. Neither do all of the occurrences yield much gold or silver. And 4. Gold and silver bearing lead ores. This class includes a variety of deposits containing much lead and also silver, with gold usually in subordinate amounts. Since gold and silver ores so vary in their mineralogical associations and richness, the metallurgical processes involved in their extraction are varied and often complex. Those ores whose precious metal contents can be readily extracted after crushing by amalgamation with quicksilver are termed free milling ores. This includes the ores which carry native gold or silver and often represent the oxidized portions of ore bodies. Others containing the gold as telluride or containing sulfides of the metals are known as refractory ores and require more complex treatment. These, after mining, are sent directly to the smelter if sufficiently rich, but if not, they are often crushed and mechanically concentrated. The smelting process is also used for mixed ores, the latter being often smelted primarily for the lead or copper contents, from which the gold or silver is then separated. Low-grade ores may first be roasted and the gold then extracted by leaching with cyanide or chlorine solutions. The introduction of the cyanide and chlorination process, which are applied chiefly to gold ores, has permitted the working of many deposits formerly looked upon as worthless, and in some regions even the mine dumps are now being worked over for their gold contents. The silver-lead ores form a large class which are widely distributed in the Cordilleran region and not only supply most of the lead mined in the United States, but in addition may also, and often do, carry variable quantities of silver, gold, and copper. The deposits as a whole present a variety of forms. The associated rocks are often faulted, and the ore bodies are commonly oxidized above, so that the altered portions require the different metallurgical treatment from the sulfide ores found below. Secondary enrichment has in some cases raised the grade of the ore. Aluminium is one of the few metals whose ores do not present a metallic appearance. Many different minerals contain aluminium, but it can be profitably extracted from only a few. Common clay, for example, presents an inexhaustible supply, but the chemical combination of the aluminium in it is such that its extraction, up to the present time, has not been found practicable. While many different minerals contain manganese, practically the only ones of commercial value are the oxides and carbonates, and in this country only the former. The silicates are not used as a source of manganese owing to their high silica percentage. The several ores of manganese are often intimately associated, the pyrolusite generally assuming a crystalline and the silomelane a massive character. Manganese oxides are also often intermixed with more or less oxide of iron, and considerable amounts of the metal are obtained from magnetiferous zinc, silver, or iron ores. Since such manganese is used in iron reduction, the last association is of importance. Mercury ores are not confined to any particular formation, but are found in rocks ranging from the Ordovician to recent age in different parts of the world. Nor are they peculiar to any special type of rock. Although igneous rocks are often found in the vicinity of them, they occur as veins, disseminations, or as masses of irregular form. The most important ore of antimony is stibnite, and the metal is rarely obtained from any other mineral, although native antimony has been sparingly found. The stibnite, together with a gangue of quartz and sometimes calcite, usually forms veins cutting igneous, sedimentary, or metamorphic rocks. Antimony has been found at a number of localities in the Cordilleran region, but the great distance of deposits from the railroad, together with the fact that the smelting plants are located in the east, make them of little commercial value, and no domestic production has been reported since 1901. Moreover, the large output of antimony ores and metal abroad, combined with low ocean freights and the absence of any import tax on crude antimony, are of themselves discouraging to domestic competition. Nickel and cobalt can best be treated together, for nearly all the ores containing one are apt to carry some of the other. And furthermore, in smelting, the two metals go into the same mat and are separated later in the refining process. The nickeliferous pyrrhotite is the most widely distributed of the nickel ores and may carry small amounts of cobalt. It is also called magnetic pyrites. The percentage of nickel ranges from a trace to 6%, but an increase above this brings it into pentlandite. The ores of platinum are native platinum and sperrylite. The former is commonly found in placer deposits, but has also been noted in basic igneous rocks rich in olivine, such as peridotite, or in serpentine derived from it. The sperrylite never occurs in large quantities, but has been found in association with nickel and copper ores. Iridosmine and osmiridium are also known to carry platinum. The nuggets found in placers are often regarded as being pure native platinum. This is only partly true. The chief ore of tin is cassiterite with 78.6% metallic tin, but owing to the presence of impurities, the ore rarely shows this composition. Its hardness, imperfect cleavage, non-magnetic character, high specific gravity, and brittleness help to distinguish it from other minerals that are liable to occur with it. Stream tin is the name applied to cassiterite found in placers. Metallurgy is defined as the art of extracting metals from their ores and adapting them to the various processes of manufacture. That this art was practiced in very early times is indicated by references to the use of metals in the oldest written records of the world's history. Among the many stages in the development of primeval man, none can have been of greater moment in the struggle for existence than the discovery of the metals and the means of working them. The names generally given to the three prehistoric periods of man's life on Earth, the Stone, the Bronze, and the Iron Age, imply the vast importance of the progressive steps from the flint knife to the bronze celt, and lastly to the keen-edged steel weapon or tool. The metals chiefly used have been gold, silver, copper, and tin, the last two forming the alloy called bronze, iron, and lead. Of all metallurgical processes, that of separating of lead from its ores is the oldest. Lead smelting was known to the ancient Hebrews, and silver ornaments were found on the site of ancient Troy that were so pure as to show that the Trojans know how to separate silver from lead. Lead ores were wrought by the ancient Egyptians perhaps 3,000 years BC. The value of iron in ancient times is well brought out by the fact that in Homer's Iliad, a mass of iron is mentioned as being one of the prizes at the funeral games of Patroclus. Metallurgical processes of the present day may be divided into mechanical and chemical. Under mechanical are included the various processes of ore dressing or concentration, the object of which is to separate nearly pure mineral from what is of little or no value. The methods of extracting metals directly from the crude ore or from the mechanically separated concentrates fall under three classes. 1. Extraction of the metal from oxides and carbonates by the reducing action of carbon and the treatment of sulfides by the oxidation of the sulfur contained. 2. The extraction of a metal by getting it in solution and replacing it by another. And 3. Amalgamation, or bringing the metal in contact with quicksilver, in which it forms an amalgam. Most metals are obtained ultimately by the use of heat, either by treating the crude ore or the concentrates obtained by some method of ore dressing. It is well, however, before beginning a discussion of the metallurgy of iron and steel, to define just what is the iron and steel of commerce and industry. In Henry Marion Howe's Iron, Steel, and Other Alloys, they are described as composites of granitic substances, intimate mechanical mixtures or conglomerates of microscopic particles of certain quite distinct, well-defined, simple substances in widely varying proportions. The chief of these substances are ferrite, the microscopic particles of nearly and perhaps perfectly pure metallic iron. It is magnetic, very soft and ductile, but relatively weak, with a tensile strength of about 45,000 pounds per square inch. It is of the isometric system. It always forms a very important part of slowly cooled iron and steel in general. Cementite, a definite carbide of iron, Fe3C, containing 6.67% of carbon, very brittle, harder than hardened steel, scratching glass and feldspar but not quartz, and magnetic. The carbon in slowly cooled steel is chiefly or wholly present as cementite. Graphite, a characteristic component of gray cast iron, of which it usually forms from 2 to 3.5%. It is pure or nearly pure carbon. When it forms during the solidification of the metal, as is usually the case, it occurs in very thin laminated plates or flakes, often 1/8 inch or more in diameter. When it forms within the solid metal at temperatures materially below the freezing point, it occurs, at least under certain conditions, in very fine powder and is then called temper graphite, the temper carbon of Ladybur. Slag, the characteristic component of wrought iron, which usually contains from 0.2 to 2% of it. It is essentially a ferrous silicate, and it is present in wrought iron simply because this variety of iron is made by welding together pasty granules of iron in a bath of such slag, without subsequently melting the resultant mass or in any other way giving the envelopes of slag thus imprisoned a chance to escape completely. The great classes of iron and steel of chief value to the engineer, and probably to the world at large, are essentially intimate mixtures or conglomerates of the first two strikingly different microscopic constituents: ferrite extremely soft and ductile, cementite extremely hard and brittle, the former like copper, the latter like glass. The properties of several of the classes may indeed be influenced, and very profoundly, by thermal and mechanical treatment, and by the presence in certain of them of slag or of graphite. But the fact of which our attention should be concentrated at first is this: that the difference in properties between the different industrial classes of iron and steel are due chiefly to differences in the ratio which the ferrite bears to the cementite. What has just been said does not apply, it is true, to what is called hardened steel, but it does apply to the great industrial classes of wrought iron and of steel, such as ship, rivet, fencing wire, tube, rail, and tin plate steel, and indeed all structural steels, whether for plates, beams, eye-bars, angle irons, or any like object. The steels which are especially soft and ductile, example the rivet and boiler plate steels, consist chiefly of the soft, ductile, copper-like ferrite, as do those with very high electric conductivity, such as telegraph and telephone wires. In these steels, the proportion of cementite may not exceed 1% of the whole, the rest consisting almost wholly of ferrite. The harder steels, like rail steels, which are called upon to resist abrasion, example the grinding action of the car wheels intensified by the presence of sand between wheel and rail, have a much larger proportion of cementite. About 93% of their total mass is made up of ferrite, and the remaining 7% consists of cementite. This quantity of cementite suffices to increase greatly the resistance to abrasion, while the loss of ductility which it causes, though very marked, is not dangerously great. Naturally, as the proportion of cementite in steel increases and that of ferrite decreases, the ductility diminishes continuously and the hardness increases continuously. The tensile strength, however, reaches a maximum when the cementite amounts to about 15% of the whole and the ferrite is about 85%. With further increase of cementite, the tensile strength again decreases. The constitution of steel is not in general reported in the percentages of ferrite and cementite, nor indeed are most engineers and metallurgists of today sufficiently familiar with the aspect of the subject to speak of it with confidence. But this is the aspect with which the practitioners of the near future must face, and it is also that which makes possible an understanding of the relation between the composition and properties of these different classes of iron and steel. Instead of saying that a certain kind of steel, for instance rail steel, contains so much cementite and so much ferrite, it is customary to report simply the carbon which that cementite represents. Graphite is an important constituent of cast iron, especially of gray cast iron, but may be regarded as either absent from steel or, if present, only in unimportant quantities. Gray cast iron, the only kind of cast iron which can be widely used by engineers, may be regarded as a conglomerate of the second degree, for it consists first of a mechanical mixture of ferrite with cementite, quite as steel does, while through this mixture as a matrix there is scattered much free carbon in the form of sheets of graphite. White cast iron typically would consist of cementite and ferrite quite as structural steel does, but with a much larger proportion of cementite, rising even to 67%, say 4.5% of carbon. Hence the extreme hardness and brittleness of this class of cast iron, so extreme as to exclude it from most engineering uses. Wrought iron consists essentially of a metallic matrix identical with low carbon steel, in which is mechanically mixed a small quantity of slag, a silicate of iron. This slag is not unimportant, yet it is far less important than the ferrite and cementite of the matrix. Steel, hardened by sudden cooling from a red heat, consists essentially of austenite, a solid solution of carbon in iron of varying degrees of concentration. When austenite contains as much as 1% of carbon, it is intensely hard and brittle, and indeed its hardness and brittleness are roughly proportional to the quantity of carbon which it contains. Hence, steel for purposes which require extreme hardness, such as files and other tools for cutting metals and even wood, have from about 3/4 to 2% of carbon, enough to give the degree of hardness required for the special purpose, but not enough to cause a prohibitory degree of brittleness, and they are hardened by sudden cooling. Besides the cutting tools, armor plate and projectiles are made of hardened steel, and therefore consist essentially of austenite. Alloy steels have come into extensive use for important special purposes, and a very great increase of their use is to be expected. The chief ones are nickel steel, manganese steel, chrome steel, molybdenum steel, and tungsten steel. The general order of merit of a given variety or specimen of iron or steel may be measured by the degree to which it combines strength and hardness with ductility. Nickel steel, which endures well the effect of sudden shock, is used widely for marine shafting. It has been used tentatively for railroads, but while it has the stiffness and resistance to wear which they require, too many rails have broken in use. As actually made, manganese steel contains about 12% of manganese and 1.5% of carbon. Its ductility, to which it owes much of its value, is profoundly affected by the rate of cooling. Sudden cooling makes the metal extremely ductile, and slow cooling makes it brittle. Its behavior in this respect is thus the opposite of that of carbon steel. Its great hardness, however, is not materially affected by the rate of cooling. It is used extensively for objects which require hardness and ductility, such as rock-crushing machinery, railway crossings, mine-car wheels, and safes. Chrome steel, which usually contains about 2% of chromium and 0.8 to 2% of carbon, owes its value to combining, when in the hardened or suddenly cooled state, intense hardness with a high elastic limit, so that it is neither deformed permanently nor cracked by extremely violent shocks. For this reason, it is the material generally, if not always, used for armor-piercing projectiles. Tungsten steel, which usually contains from 5 to 10 and sometimes even 24% of tungsten and from 0.4 to 2% of carbon, is used for magnets because of its great retentivity, and for lathe and similar metal cutting tools, which are to cut off a very thick slice at each stroke. The great friction due to the thickness of the cut heats the tool to a temperature at which the temper of common or carbon steel is drawn. The merit of tungsten steel is that, like manganese steel, it retains its extreme hardness even after it has been heated to 400 degrees centigrade, or 752 degrees Fahrenheit. Under these conditions, the Taylor and White variety retains its cutting power even when the friction is so great that the chips of metal cut are so hot as to glow visibly, and even the edge of the tool itself grows red hot. Molybdenum steel is now often used instead of tungsten, 1% of the former element replacing 2% of the latter, so that the ratio between their effects appears to be that which their atomic weights would indicate is probable. In other words, 1 molecule of molybdenum appears to have the same effect as 1 molecule of tungsten. Today, practically all of the iron ore mined is smelted in the iron blast furnace and there converted into cast or pig iron. And this is the case whether the resultant iron is to be used in the form of cast iron or whether it is to be converted into one of the two other great commercial classes of iron, wrought iron and steel. It is true that there are many direct processes by which wrought iron or steel may be made directly from the ore without first converting it into cast iron. For example, without first putting it into more carbon and silicon than it needs in its finished form, and then taking them out at great expense. But the processes of today are a little more than historical of scientific interest. Whatever promise that they may have made in recent decades has been killed by the great cheapening of the blast furnace process. The blast furnace is an enormous shaft, in many cases as much as 100 feet high and 25 feet maximum inside diameter. The furnace is at all times full from top to bottom of a column consisting of coke or other fuel, limestone, and iron ore, though the lower part of this column consists of fuel only. The ore, flux, and fuel are charged through a hopper at the top of the furnace and form a continuous column extending from the top to the bottom. Through openings called tuyeres at the bottom of the furnace, a powerful blast of air, usually highly preheated, is introduced. This burns the fuel, thereby generating an intensely high temperature sufficient to melt the ore, the iron of which has, by the time it has descended to this region, become reduced to the metallic state. Thus the whole column of solid materials descends slowly as its lower end is eaten away, the fuel which it contains being burned away by the blast and the rest of the material being melted away by the heat from the combustion of this fuel. In addition to the descending column of solid material, there is an ascending column of hot gases. The oxygen of the blast introduced at the tuyeres is quickly converted into carbonic oxide by its reaction with the carbon of the fuel which it there meets. Very soon after entering the furnace through the tuyeres, the atmospheric oxygen has been converted into carbonic oxide, which, together with the atmospheric nitrogen of the blast, sweeps up through the furnace in enormous columns at great velocity. There is thus two columns moving in opposite directions, a solid column of ore, flux, and fuel descending very slowly, and a swiftly rising column of hot gases. Any given lump of the solid material passes through the furnace in about 12 to 15 hours, while any given particle of oxygen or nitrogen entering at the tuyeres passes through and quickly escapes at the top, its passage occupying probably only a small fraction of a minute. The iron ore always contains, besides iron oxide, a considerable quantity of siliceous or earthy material called gangue, and the fuel also contains a certain amount of ash. These materials, the gangue and the ash, together with the lime of the limestone, unite to form a single molten mass, the slag, which floats on the top of the molten iron. Two deep holes are provided at the lower end of the furnace, one called the tap hole, at its very bottom for drawing off the molten iron at intervals, and the other called the cinder notch, a very little above this for drawing off the molten slag. These holes are closed with plugs of clay, except at a time when the molten materials are drawn through them. While these two columns, the descending solids and the ascending gases, pass each other, and the hot gas is sweeping up swiftly, the initially cold solid materials descending slowly, the heat of the gaseous column is recovered by being transferred to the descending solids, so that although the temperature of the gases in the neighborhood of the tuyeres is about 2,912 degrees Fahrenheit, the temperature of those which escape from the top of the furnace is only about 572 to 752 Fahrenheit, owing to the fact that the fuel is burned in immediate contact with the solid materials which it is to heat, and that the products of the combustion are thoroughly cooled in their long upward travel, in which they are exposed to cooler and cooler masses of descending solid materials. The thermal efficiency of the blast furnace is very high. The purifying reactions are brought about by 1. In the puddling process by stirring iron oxide in the form of a silicate very rich in that oxide into the molten cast iron as it lies in the thin boiling layer on the hearth of the reverberatory furnace. 2. In the Bessemer process by blowing cold atmospheric air through the molten cast iron in a deep clay-lined or dolomite-lined retort called a converter, the rapidity of the oxidation itself raising the temperature rapidly. And 3. In the open hearth process by exposing the molten cast iron in a thin and very broad layer on the bottom of the reverberatory furnace to an overlying layer of slag containing iron oxide, and usually enriched in that oxide by throwing into lumps of iron ore. In the last process, in addition to this purification of the cast iron by these oxidizing reactions, its impurities are in most cases also greatly diluted by adding much relatively pure steel scrap. If steel is cooled suddenly, it is thereby made harder and less ductile, or even extremely brittle, and it is said to be hardened. The degree to which it is thus hardened increases with the carbon content, so that whereas very low carbon steel is affected only very slightly, steel with 1% of carbon is made as hard and nearly as brittle as glass. The hardness and brittleness induced increase with the rapidity of cooling without limit, but they are apparently nearly independent of the temperature from which the sudden cooling begins. The tensile strength at first increases with the intensity of hardening, but reaches a maximum and then declines. In case of high carbon steel, a moderate rapidity of cooling may give the highest tensile strength, but in the case of low carbon steel, the tensile strength seems to increase with rapidity of cooling without limit. Hardened steel is tempered, that is, the hardening is mitigated or let down by slight reheating, say to 200 or 300 degrees, and the steel is annealed. That is, the hardening is completely removed by reheating farther, say to 600 degrees. After this reheating to 200 or 300 degrees, it is immaterial whether the steel is then cooled suddenly or slowly. The degree of tempering is the same in either case, and the same is substantially true of the higher heating to 600 degrees or annealing. All the best cutlery and tool steel is made by the crucible process, and indeed all for which any considerable excellence is claimed is supposed to be, though often incorrectly. But the great mass of the steel of commerce is made by the Bessemer and the open hearth process, the latter being generally considered the best, and rising from 9 to 53% in the United States, it reveals in a wonderfully true proportion the advance of progress. End of section 32. End of The Science History of the Universe, Volume 2, by Francis Rolt-Wheeler.